Welcome to Friction. For our first problem, we have several parts. It is a wooden pallet carrying a load of 600 kilograms, rests on a wooden floor. Keyword, rests. A forklift driver decides to push it without lifting it, so he's just pushing it while it's on the floor. A, what force must be applied just to get the pallet moving? B, after the pallet begins to move, what will be its speed after half a second? And C, if the forklift stops pushing after that half second, how far does the pallet slide before coming to a stop? So let's go ahead and break up this problem into small, bite-sized chunks. First, let's figure out what force must be applied just to get the pallet moving. So we'll start, since we're working with forces, by drawing a free body diagram. So we have our 600 kilogram pallet here, and that pallet has a specific gravity going down, a force of gravity, a force normal resisting that gravity, being pushed, the pallet is being pushed up on by the floor as hard as it's pushing on the floor. It has an F1 force, that's the force applied by the forklift driver, and it has a resistive force of friction. And then we're going to have a total F net, but that's going to come in later. Right now, we're just trying to see at what force for force 1 will it be enough to overcome the force of static friction. So let's go ahead and put an S there too to signify static friction. Force of friction, static. So we have 4 forces we're working with here. Let's make a variable list of those 4 forces. First we have Fg, Fn, F1, F friction, static. And then, let's go ahead and put in our coefficients of friction. Now I know, because I've read part B and C, I'm going to be dealing with 2 coefficients of friction. I'm going to be dealing with mu s and mu k. I like my s's to be a little smaller than that. Okay, and then I need to know the mass. So I should have a mass variable in here. And now my force of gravity is going to be that mass times the acceleration due to gravity. And just so I can keep it separate from all of my other accelerations, because the force of gravity is always going to be 9.8 on the Earth, I'm going to use a lowercase g to signify it. Okay? So g is acceleration due to gravity. So that'll help me keep that straight. So what force must be applied just to get the pallet moving? Well, the force that needs to be applied just to get the pallet moving is going to be when F1 is equal and opposite to the force of friction static. So F1 needs to be equal and opposite, so negative, force of friction static. If we were working with equilibriums or anything, then we would have, we wouldn't have to worry about this negative. But we're working with I'm not going to mention that. So F1 equals negative, force of friction, static. So what is the force of friction static equal to? Force of friction static is equal to mu s times force normal. And in this case, force normal is just equal and opposite to force of gravity. So at this point, Fn equals Fg, and is the opposite of it. Okay, great. Fg is equal to mg. So mass times the force of gravity. Okay, there we go. We have 4 equations that we can just roll all into one. So F1 is going to be equal to, okay, we'll plug in this for this. Okay, we're saying negative, okay, great. Because Fg is going down, so that's going to be negative. This is going up, so that's going to be positive. Okay, so putting that in for Fn, and then Fn is going to be right here, and then that's just going to plug in for that. Okay. So negative force of friction static times US times Fn is going to be this negative mg. Okay. Whew. That actually ends up not being too bad because all of our force equations actually end up being pretty simple. So let's go ahead. We've got a negative and a negative because this is a negative. So those multiplied together are going to be positives. Great. Very nice, very nice. Okay, before I go any further, I've gone quite a bit before putting the numbers into my variable list. I got a little gung-ho here, so let's go ahead and make sure we do that before we do anything else. My mass, 600 kilograms. My force of my acceleration due to gravity is 9.8 meters per second squared. My coefficient of static friction is 0.5. My coefficient of kinetic friction is 0.2. Okay. Let's go ahead and plug our numbers in here. So we've got F1 equal to negative 0.5 times mass, which is 600, times a negative 9.8. Negative because it's going down. Okay. So 9.8 times 600 times 0.5. Notice I've got two negatives, so they're going to cancel each other out. Beautiful. So that's going to get me a result of 2,940 newtons. It's equal to F1. Okay. So that's the force that needs to be applied just to get the pallet moving. Let's go ahead and put that in there. 2,940 newtons. Okay. Now, that's going to be my force of static friction. Let's go ahead and use these two numbers to calculate my force of gravity and my force normal, because I'm going to need those numbers later. So 600 times 9.8 is going to get me, for force of gravity, negative 5,880 newtons. Force normal, it's going to be positive 5,880 newtons. Okay, fantastic. Force of static friction, that's going to be negative 2,940 newtons. Perfect. 0. There we go. Okay, so let's move on to part B. So that was all part A. Part B adds a kinematic component to it. After the pallet begins to move, what will be its speed after half a second? So, for this, what we need is an F net. Okay? Now trust me on this, we're going to need an F net. Because what we're going to end up needing to do is use that F net to calculate the acceleration that it's moving at. But that F net is going to be this F1 minus the force of kinetic friction. So we're going to need that as well. Force of kinetic friction. And then we'll need, well, if we need kinetic friction, we need coefficient of kinetic friction. Okay, what else? What else do we need? We need mass, obviously, because F equals ma. Okay. Is there anything else we need? Anything else we need on the forces side? Well, I need F1 because I'm going to need to subtract the force of kinetic friction from F1 to get F net. Okay. What else? Well, I'm going to need Fn to calculate that. Okay. Force normal. All right, that should be good for the forces. Let's put our kinematics in here. So S, Xi, Vi, Vf, At. Okay, so our F1, okay, we already know that. That's 2,940 newtons. Our mass is 600 kilograms. Our UK is 0.2. Force normal, we already calculated that as well, 5,880 newtons. Our initial velocity is 0. Our initial position is 0. Okay, well that's nice, that's nice. Our time is 0.5 seconds. That's also nice. Okay, it looks like I have enough values to solve for force of kinetic friction, and then F net, then acceleration, and then my final velocity. Okay. All right, so that's my process here. So let's start over here. Let's first find our force of kinetic friction. F of friction, kinetic, is going to be equal to, well, it's going to be my force normal times my coefficient, kinetic friction. Okay, that's nice. That's nice and simple. Got those numbers, 5880 times 0.2. All right. I hope you guys are starting to see that once we get this set up, it's actually becoming pretty easy because everything is just F equals ma, or friction is the force normal times the coefficient. So the equations have condensed a lot. We just end up having a lot more variables, and our skill that we really need to build is drawing these free body diagrams and identifying the forces that are present. If you can get that down, these actually become really easy. As long as you've got this setup good, and you've got your free body diagrams good, the rest of this is a breeze. Okay, so let's calculate our force of friction for kinetic. And that's going to end up with a 1,176 newtons. Excellent. And then our F net is just an addition equation. It's just adding these together. So our F net is going to be our F1 plus, let's go ahead and say that's negative because it's going that direction, plus FKF. Okay, so F net is 2940 plus a negative 1,176. Okay, what is that equal to? That's going to get us a 1764. Great year. Okay, so 1764 newtons. Now we can use that F net to find MA. We already have the mass. The mass is 600 kilograms. So we're just going to take that 1764 divided by 600. That's going to give us our acceleration. All right. Just 3 short problems gets us all the way to our kinematics. All right, and that gets us 2.94 for our acceleration. So 2.94 meters per second squared. So now VF is easy because VF equal to AT plus VI. VI is 0, so it's just AT. So we know 0.5 seconds, 2.94 times 0.5 is just going to be 1.47 meters per second. Bingo bango. There we go, that's part B. All right, let's box this off. And let's work on part C. So part C, I let the box go. So what we're going to have there is we're going to have a force of friction, and we're going to lose our F1. So we'll have a new free body diagram here that's still going to have the force of gravity, still going to have the force normal, still going to have that force of kinetic friction, but it's not going to have the F1. So it's just going to have that force of kinetic friction causing a deceleration. So what we need to know is force of kinetic friction. We don't really need to know Fn because we already have our kinetic friction force. We don't need to know Fg. What we need is the mass and the acceleration. Okay? And what we want to know is how long does it take to come to a stop? Okay. So then we'll have our kinematic variables, so S, Xi, Vi, Vf, and we already have A, so T. We want to know T. So in this problem, force of kinetic friction, that is 1,176 newtons. And that's a negative. Remember, that's a negative. It's going to our negative direction. Our mass, still 600 kilograms. That never changed. Our acceleration is going to be new. Our xi, well, our xi we'll say is 0. We want to know how far it slides after we let it go. So the point where we let it go, that's when it turns 0. Okay? So then our vi is the final velocity we just calculated, 1.47 meters per second. And our vf, well, that's 0. Because we're wondering when it comes to a stop. Okay. Well, I can already see that I'm going to determine my acceleration, and then I'm going to find my time. So I'm going to use F equals ma, and then I'm going to use A equals Vf minus Vi over T. Excellent. So F equals ma, it's going to be force of friction, kinetic, equals ma, and I have this force, so that's going to be negative 1176 equals 600 A. So let's go ahead and calculate. Acceleration is going to be negative 1.96 meters per second squared. Then I can plug that in over here. So I'm going to solve for t. Okay. Oh, hey, there we go. All right, Vf, that's going to be 0. So 0 minus 1.47 for my Vi over negative 1.96. That makes sense because I'm going to end up with a negative divided by a negative, which is going to give me a positive time, as it should. That makes sense. Great, so 1.47 divided by 1.96. That was 9, not 1.96. 0.75 seconds. And there we go. We've solved this whole problem. Now this one was long, this one was a doozy. But I hope you've seen that just setting it up properly, taking it one step at a time, really breaks this up into some problems that aren't actually that difficult to solve mathematically. The physics is really getting into the challenges thinking about it, and less in the equations themselves. So let's get some more practice doing these before we get into the factors of trigonometry that we'll be adding into this. All right, thanks guys.